Okay, here we go. Sorry for the delay. For some reason, my YouTube streaming program didn't want to cooperate this morning. So let me know. Give me a thumbs up if you can see this, so I know that this is actually coming through. If you can hear me, excellent, perfect. So then let's get started. As you noticed, we started a new chapter today, and the chapter is titled Work and Kinetic Energy. So today we're going to talk about work and kinetic energy. And obviously, we're going to do a little bit more than just introducing the terms. And actually, we're going to talk pretty much on Friday then about the work energy theorem. Actually, maybe we'll get to it today, which is how we combine work and kinetic energy in solving problems. So let's start with the definition of work. And sort of the informal definition is that work is the amount of energy that is transferred to an object when a force is working on it. In particular, it is the amount of energy transferred when that force causes the object to move and to be displaced. So it's when the force causes displacement, then the work is the amount of energy that's transferred to that object. So we can actually look at that. First we'll introduce it sort of theoretically in a general sense, and then we'll apply it in some situations that are easier to interpret. So let's imagine we have an object that we're moving under the influence of a force F from point A to point B along a certain path. In some places, the force might be in the same direction of the displacement. In other places along the path, the force might be maybe perpendicular to the displacement, or even for some amount of time, the force might actually be in the opposite direction of the displacement. That, of course, would likely cause the object to decelerate, to have an acceleration in the opposite direction as its current motion. But all of those are possible. All of those are possible ways in which the force can be oriented along the direction of this path. So now we're going to look at an infinitesimal segment on this path, a very short segment on the path between A and B. And for that infinitesimal segment, we can introduce the work done during that infinitesimal segment as a relation, as an equation that involves both the infinitesimal displacement and the force. And actually, we're going to write this down here. So the work in an infinitesimal segment along a path, that is, so it's an infinitesimal amount of work, so we're going to call it dW to indicate that it's an infinitesimal quantity. We add the d here. So that's going to be the force dot product the displacement. So when we go back to the slide, the force dot product the displacement, or the infinitesimal displacement, will be the infinitesimal amount of work. And so you can already see the dot product will cause the infinitesimal amount of work to be 0 when that angle is 90 degrees. And it will be maximized for constant force and displacement when the angle is 0, or when, in other words, the force and the displacement are parallel instantaneously. So that's the infinitesimal amount. Now, to get to the total work along the entire path, we have to integrate this. So for those of you who are in calculus right now, can you give me a thumbs up if you have seen already something about integrals? Not seeing any thumbs ups. Okay, well, maybe 2 thumbs ups. Okay, some of you are realizing that maybe you have seen it. Okay, good. In any case, the work, or this integral, is essentially the sum of all the little dWs. So the total amount of work is, in some sense, I'm going to put this in quotes here, it's the quote the sum over all the amounts of infinitesimal work. So that's going to be the integral from A to B of dW, and in other words, is the integral from A to B of F dr, right? Okay, yeah. So you haven't seen integrals yet, but think of this as just, you know, essentially a sum over infinitesimally small quantities. Let me see if I actually have a slide that demonstrates that. Not really. Okay. You know what? I'm just gonna quickly copy a slide in here that hopefully will make this clear. So let's see. Copy. Come on. Paste. There we go. So that's gonna be work as integral. Sorry for the on the fly editing here. So the work is the integral of and essentially the amount of surface area underneath the curve of the force as the object is going through displacement. So if we go back to the slide here, that's what that integral means. And so we have our force dot product with the infinitesimal displacement, and that turns into the description of an integral. In our integrals, I mean, in this case, this is a fairly complicated integral. This could be complicated. Remember that f can, of course, be something that depends on the position. It could depend on the time. And so then we're integrating that after doing a dot product. This is going to introduce some cosine theta, and then the theta, of course, is going to depend on the position and the time. So all of this could be fairly complicated, but what we will fortunately be able to do is often we can either choose the path or choose at least the coordinates. So the integral becomes easy. Or the other thing that we will often do is the force will be constant. And of course, when the force is constant, then the integral doesn't involve any calculus in this force here. So we're just going to be able to bring the force out of the integral. We get our integral that is now just over the line element, and this is actually going to turn into the length from A to B in absolute value. So that's the path length. So that's going to become a much easier expression to deal with. So in both cases, we are going to want to simplify our expression for the work so that it is actually easier to calculate. So for example, in the first case here, if we have motion on a circle, for example, in uniform circular motion, then we're going to use polar coordinates. So then everything will just depend on the angle phi, and that will simplify the integral. Okay, so we've introduced work. We've kind of introduced it already as, well, I didn't write down the definition, but we've introduced it as the energy that is transferred to an object. So this is going to have dimensions of energy. And what are dimensions of energy? Well, let's look at this. We have a force times the distance. In the infinitesimal description here, we have a force times the distance. So the unit of W will be force times distance, dr. So that's going to be newtons times meter. The units of work are newtons times meter, or what we call the joule, so J. Okay. Um, so I already said that constant forces is going to be one way that we simplify that. We can actually take this a little bit further, and actually let's treat this explicitly here. For a constant force along a constant force with some displacement, we're just going to have that the work is now the force times the integral from a to b of dr, and that's going to be the force times this displacement from a to b, or f dot r b minus ra in vectors. So the displacement from a to b is the position at b minus the position at a. And so one thing we notice here immediately is that this depends only on the position A and the position B, but not on the exact path that is taken. So if we look at that, if we look at this integral, the fact that the constant force could be brought outside of the integral actually means that the work only depends on the positions A and B. It doesn't depend on the exact path we take to go from A to B. So if we go back to our drawing here, it doesn't matter what path we take, all of the different paths that we would take for a constant force, all of the different paths we can imagine, they will all result in the same in the same work. And this is an important property for some class of forces that we will talk about, which isn't true in general, but it is true for a specific set of forces, and constant forces are one of them. So where would this this show up? Constant forces. So let's see, this is more about integrals. So if we have a person pushing a lawnmower, for example, let's say they're pushing down at an angle theta against the lawnmower, and there's displacement in the horizontal direction. So what will happen is, or displacement d and the force F will be at an angle theta. So in the case of the lawnmower example, or F or work is F times the displacement. So that will be the force times the magnitude of d times the cosine of the angle between the force and the displacement. So one of the things you'll see is that if we push down vertically, then of course, first of all, there won't be a whole lot of displacement. But even if there was displacement, the displacement would not be caused by us or by the person pushing down. It would be caused by a different force. So this force, the force pushing down, would not be the one that does work. And so indeed we would find 0 because theta is 90 degrees. And at 90 degrees, we of course have a cosine that's equal to 0. So at 90 degrees, so this is pushing down, but still horizontal displacement. So in this case, W is equal to 0. F does not do work. And this is actually a fairly common situation where the force and the displacement are perpendicular to each other. We don't just have to look at the lawnmower. The other example here is someone holding a briefcase, and so what this person is doing is exerting a force upward on the handle of the briefcase. And so if this person is standing still, she's not exerting any work because the displacement is 0. But even if she's walking horizontally, since the angle is 90 degrees between the force that she's exerting and the displacement, the work is actually zero. So there's no work that is being done by this force against if the displacement is in the horizontal direction. If there's a displacement that is in the vertical direction, then of course there will be work done, because then this angle theta is not equal to 90 degrees anymore, and then there will be a non-zero work. Okay. So if so in this case we were at an angle of 90 degrees. Let's look at the other extreme, an angle of 0 degrees. So let's go back to our lawnmower example here. So an angle of 0 degrees would correspond to pushing completely horizontally. So now the force is along the horizontal direction. So all of the force is pointing along the direction of the displacement. And in this case, the force, in this case, the work just becomes the product of F and D, because, of course, the cosine of 0 degrees is equal to 1. So if we wanted to maximize the work that is done by the force that we're exerting on this lawnmower, then we would want to push along the direction of the displacement. So we've learned a few things. Maximizing the work involves making sure that the force and the displacement are aligned. If there's a force that is normal to the displacement, then there's no work being done. So can we think of any forces that we've talked about that are always normal to the displacement? And I'm stressing normal there because it's a clue. So which forces are always normal to the direction of displacement? So indeed, normal forces are normal to the direction of displacement. If we look at an example of a normal force, which was, of course, a mass, for example, sliding down an inclined plane, right? So in this case, the normal force is in this direction, perpendicular to the direction of motion, as long as, of course, this object is sliding down this this slope. So in this case, the normal force and the displacement, let's call this dx, and the normal force are perpendicular. Let's call it dr actually, just to have a vector quantity there, not just a single coordinate. So if this is dw, then of course the work is equal to 0, since these are perpendicular to each other. So normal forces do not do any work. Someone brought up the example of a centripetal force. Excellent. A centripetal force. In this case, we have a trajectory that's along a circle. So our displacement, dr, will be normal to the centripetal force. Again, remember, the centripetal force is the net force of all forces working on an object. And so in this case, again, if we look at uniform circular motion, then Fc is perpendicular to dr, and then of course the work is equal to 0 as well. So centripetal forces in uniform circular motion do not do work. Why do I stress here that this is uniform circular motion? So of course we we talked about other non-uniform circular motion. And in the case of non-uniform circular motion, we said there had to be both a tangential and a point, an acceleration that points to the center. So in the general case, a is equal to AC plus a perpendicular, or I think maybe we called it AT, where we have a tangential part and a centripetal part. In the case of uniform circular motion, the tangential part is equal to 0. And of course, the tangential part, that is the part that actually would require a component of the force that is along the tangential direction. And so there would be a non-zero component to the work. And so in the case of a non-uniform circular motion, there will be work done by the component of the net force that is along the tangent, the tangential direction. So let's think about another type of force. We've talked about friction. And in particular, we've introduced friction as, for example, in the case of kinetic friction, as a constant. And in this case, we picked mu k times n, which is really just the magnitude. And it's in the direction opposite to the direction of motion. So I'm just going to be a little bit cavalier with my notation. I'm just going to put a minus sign here to indicate that this is in the direction opposite the direction of motion. So opposite direction of motion. So in this case, if we have, for example, the textbook uses an example where someone's taking their couch and moving it, sliding it along the floor to here, and then sliding it sideways to point B, and then the person decides that the couch doesn't fit there, and the person slides the couch back to point A. So this person has moved the couch in a closed trajectory from A through this point in the corner here to B and back to A. What is going to be the work done by friction on this trajectory? You know, in words, we don't have enough numbers here to calculate it. But what will the force due to friction in particular, will it be 0? So friction is going to have the force due to friction is going to be in the opposite direction of motion, opposite to the direction of motion. But it is going to be parallel to the direction of motion. So in this case, if we calculate the work done due to kinetic friction, we're going to have a force due to friction, which is constant. And it will be in the direction of motion, but in the opposite sense. So it will always be at a theta of 180 degrees. So the cosine of theta will be -1. And the part that we still have missing here is our integral over dr. And that's going to give us the total distance from point A to point B, for example. Of course, in this case, I probably shouldn't use A, B. Let's just keep it at L as the length. So if we're going to move our couch from A to the corner here, we're going to move the couch here against the direction of friction. That's going to give us negative work done by friction. And the amount will be the force of friction, the magnitude of friction, times the distance, 3 meters. Then we're going to have another stretch here. The same force of friction will apply. I mean, we're still sliding things over the floor. Let's assume that the normal force hasn't changed. The weight of the couch hasn't changed. So now we're going to have the force of friction times the length of the displacement, 1 meter, and we're going to get here. And then on the way back, we're going to have, 3 squared plus 1 squared with a square root. So what's that? That's pi, right? Because pi is the square root of 10, or approximately so at least. So we're going to have the distance here times the force of friction to get back to point A. So in the case of the problem of moving the couch from A to the corner to B back to A, the total work is going to be 3 meters times the force of friction in the negative, with the negative sign because of my 180 degrees, plus 1 meter times the force of friction with a negative sign. So I'm going to take the minus sign here, minus ultimately then square root of 10 meters times Fk with a minus sign as well. So the total amount of friction is going to be just the total distance times the force of friction with a negative sign. The negative sign indicates, so the fact that this is negative indicates that work is not being done by friction, but another force has to do work. And of course, what's that force? That's the person pushing the couch around, right? That's the force that someone is exerting while pushing the couch from one place to another. That is the force that is doing work. Friction is not doing work, but work is being done against the direction of friction. So this is clearly one example where the path itself matters. If we go from A through this corner, through B and back, it would have mattered if we took a longer path. As you know, if you want to move something around and you're working against friction, you're sliding things on the ground, you want to take the shortest path to exert the least amount of energy, in other words, with your force with which you're pushing, to apply as little as possible work when you're moving things around. So this is an example of one of those forces where we don't, where we are dependent on the path. So in this case, friction. In the case of friction, work depends on the path. And this is an example of a dissipative force, which is in contrast with a conservative force. A conservative force is a force that does not dissipate energy, it conserves energy. So energy is, well, let me not write that in those terms, but does not dissipate energy. And an example of a conservative force, this is the kind of forces where the work does not depend on the path. And an example there is the gravitational force. So let's now look, this was a trajectory along, a closed path. We can go to this example. It's exactly the same trajectory, but the example now is someone taking a book off the shelf, reading it. Well, actually, they're taking it off the shelf at A, bringing it down 1 meter, moving it over 3 meters here, and then moving it back at the end of the trajectory. So what's the work done by the force of gravity on this book? Well, we're going to have the force of gravity is pointing down. So for the stretch here from A downwards, we're going to have an angle that is 0 degrees. The direction of the displacement over 1 meter is perfectly parallel to the direction of the force. Then we have a stretch where the direction of the displacement is perpendicular to the direction of the force, so there will be no work done here. And now we're going to have a stretch here where there's a little bit of an angle. We could calculate what angle theta this would be, but ultimately what we'll see is that everything only the amount of force that is exerted, the amount of work that is done to get back from B at the table to the shelf is going to be the exact amount that is opposite to the amount of work that was done to get from A to this point 1 meter lower. So let's look at the general example, or the general expression for the work done by the gravitational force when we change the when there's a displacement. So for the gravitational force, so the gravitational force, so the work is now the force times the displacement, right? Because the force is constant, and it's also in a constant direction. So this will be minus mg in the y direction. That's the force. Dotted the displacement. That's r2 minus r1. And since we have our unit vector in the y direction, and we dot this into our vectors, we're actually going to get minus mg y2 minus y1. So the work only depends on the y component of the positions of the initial and the final point. So what does that mean? Well, it means that if we go from a point at one height to a point at another height, the only thing that matters is the height. It doesn't matter whether we also move horizontally or not. So if we go from point A to the point below here, 1 meter, the difference between y1 and y2 will be 1 meter, and y2 will be lower. If we go from point B back to point A, the difference in y is still 1 meter. Now, of course, y2 will be higher. So we're going to have the opposite work that is being done in this trajectory from B to A as it was from A to 1 meter downwards. So all of this to indicate that this is an example of a conservative force, where if we do this closed path, we end up not doing any work in total. All of the work that is being done in one part of the path is cancelled by the work that is being done in another part of the path. So we've done, there's one more force that we haven't talked about yet, and that's the work by the spring force. And it actually makes sense to think a little bit about that, because it will get us at some point to conservative energy, to potential energy. So what is the work done by the spring force when we take a spring and pull it out of its equilibrium state in panel A here to a position that is a delta x displaced from the equilibrium? So the force will be minus k times delta x at this endpoint. But of course, as we pull the spring outwards, that force only slowly builds up, right? So we're going to actually have to do an integral here. So we're going to do the spring force. So the work to get to delta x will be the integral of f dx. I'm not going to write the dot product here because we're all in one direction. The forces and the displacements are all in the same direction, so the angles are not going to play a role. And the force is minus k times delta x. And I'm going to start at x equals 0 at the equilibrium here. So delta x is actually equal to the coordinate x. So this is minus kx, that's the force, dx. And I start at, let's say, point A, and I go to point B, start at point A, and go to point B. So I can bring the constants out front, that's my minus k, and then I have the integral from A to B of x dx. And those of you who have seen calculus will know that this is minus k times x squared over 2 evaluated between A and B. So that's minus k with 1/2 xb squared minus xa squared. So that's our expression for the work done by the spring force when I pull the spring from point A, from coordinate xa, to point B, coordinate xb. So if we start, for example, at xa is equal to 0 and xb equal to just x, then we'll find that the work is minus 1/2 kx squared, right? So that's the work done by the spring force, and it's negative because we are working against the spring force to, for example, pull the spring out by a distance x. Note, by the way, that this only depends on the starting point and the ending point. On the points A and B. It doesn't depend on exactly what path we took to get from A to B, whether we did this quickly, slowly. The only thing it depends on is the paths A and B. So you don't have to remember how we do this derivation, but remember this kind of formula. Well, I guess remember is a big word for an open book exam, but make sure that you understand what this formula means, the work done by the spring force. Okay, so this is pretty much all we wanted to talk about in terms of work for now. Yeah, and someone's asking what happens if k is not a constant, if k is actually dependent on the extension. Well, then this would become, of course, a little bit more difficult. Let's say if the spring constant or the spring force as a function of x is not equal to k times or minus k times x, but let's say there's another k prime x to the third power there, then you can plug in all of this in your integral. So the work would then become the integral of minus kx minus k prime x to the third dx, and then you can calculate that integral, and of course it would have an x to the fourth term here. You'd find the work is minus 1/2 kx squared minus 1/4 k prime x to the fourth, or something like that. Just doing this off the top of my head. So this is not, of course, something you need to worry about, because that depends too much on calculus and on integrals. But yeah, that's a good question. Okay, the last concept I want to introduce in today's class is kinetic energy, and I don't actually have the formula for kinetic energy, so let me just write this down here. So kinetic energy is the energy in the motion of an object. That's the energy in the motion of an object. So this is different from work. Work is the energy that a force imparts on an object. The kinetic energy is the energy in the motion of an object. So this, of course, kinetic energy, that's a concept in kinematics, because it doesn't actually depend on using forces. The work is a concept in dynamics because it depends on the forces that apply to an object. And kinetic energy, we'll give it the symbol K, is defined as 1/2 mass times velocity squared, or of course speed squared, because at this point it becomes a scalar quantity, and the velocity and the vector nature is not important. We can also write this in terms of the momentum, which we already introduced. So we can write this as 1/2 m, and then the velocity is the momentum over m squared. So we find that this is p squared over 2m, which may be another useful way of putting this, because now it depends on the momentum. So the kinetic energy depends on the mass and the velocity. So an object with a larger velocity and equal mass will have a higher kinetic energy. If you go faster in your car, you'll have more kinetic energy. If you're going just as fast as a truck, the truck will have more kinetic energy because it has a larger mass. So that's what's that's how kinetic energy behaves, right? The units of kinetic energy are, well, they must be kilograms times meters per second squared, right? And actually, if we think about that, that's kilograms times meters per second squared times meters. And this, we know, is mass times acceleration, so that's newtons. And newtons times mass, that's the same units that we had in force times displacement for work. So this is also going to be in units of joules. So it's going to be in units of energy. So one of the things we'll want to do in the next in the next lecture on Friday is combine the concept of kinetic energy with the concept of work. And what we will realize is that the amount of work that is done on an object will be exactly the same as the change in the kinetic energy of that object. So if work is done on an object, it will change the kinetic energy, and it will change that, usually, at least, it will change the velocity of the object. And we'll come back to that on Friday. Okay, that's it for now. So see you all on Friday, and yeah, talk to you then.